So, or you can stand. It's fine.
I think this yet.
Okay. All right. So, welcome to Cosmic Conversations for tonight. Our speaker today is Alex Sehlke, who is a PhD student in the Geological Sciences Department here at the University of Missouri. Alex is originally from Germany. He did his undergraduate and diploma, kind of like a master's, in Germany. Although while he was doing his diploma, he came and visited MU for a few weeks to do some experiments in my lab. And he liked MU so much that he then decided to come back here for a PhD. And he's looking at the rheology of lava. And so far he's done quite a lot of that in the lab. He's also got to do it in the field in Guatemala, in Hawaii, and sure he'll show you some pictures of that. Today he's going to talk about rheology, lava, and the rheology of things that you may be more familiar with and are safer to play with as well. So, anyway, off you go.
All right, thanks for the introduction. My topic for today is this: planetary volcanism, why lava on Earth, other planets and moons behaves like something that you know is actually syrup, ketchup, or even toothpaste. Something that you might not think about, but I will explain how and why that is. So, first of all, what's the significance of volcanism or volcanology? So, it's to understand the environment that we live in, and there are lots of factors that volcanoes affect our life. So the first thing is a hazard potential. You can see in here, that's the volcano Mount Nyiragongo, which is in Central Africa. And there's a big city around it. Almost 1 million people live there, just right on the foot of that volcano. And this volcano is really active. And once it's erupting, as you can see in here, which is really bright, the lava flow just goes down the hill and destroys the city. So there's always the potential of destruction around volcanoes. So it's important to understand how they work. And you can see in here, it's like this whole city has been destroyed, and about 10,000 homes have been destroyed, and I think about 30,000 people had to be relocated just because of one single eruption in a day. The other reason is not just locally, it's also globally, and this is something that happened in 2010 across Europe, and it also affected me. Once when I lived there, it was this volcano in Iceland, which is up here, erupted really violently. There was just a big ash cloud, so that's meaning there's lots of little particles, grain size, dust size, big particles that just go in the air, and it's just like it's a huge dust cloud coming all across the ocean, just like dispersing in the atmosphere. It's not that it was really dark over there. It was more that this stuff was in the air, and airplanes had to be on the ground for almost a week, so there was a big economic factor, an impact that planes couldn't fly all across Europe. So there's also this kind of threat from volcanoes. As you also can see it in here, you see airplanes in Guatemala, you can see covered with black ash from volcanoes, and here in South Argentina. So this is really dangerous once that gets in the turbines. You don't know what happens with the airplane, so we better don't fly. The other thing, why would we study volcanoes on other planets and moons? Because obviously we don't live there, so we just couldn't care. But it's more the thing about the general understanding how our solar system has been evolved and where is it going over time. So what's the origin? And once we find rocky bodies, that's what I'm going to talk about. How similar are they actually to Earth? Because then we can think about one step ahead. You can see in here that's a drawing of Mars, where we potentially could colonize on Mars based on volcanic features that are so in the surrounding of a volcano, which are lava tubes. You can see in here, which is pretty small, so there's a person sitting in there. But it also can be pretty big, like this one here in New Mexico, you can see people walking around. And this is where I have been over spring break this year. And just imagine, like, if you find something like this, it might be easier just to colonize down in a cave that's already there instead of building something on the surface, because it gives you protection already. So, good thing is it's protecting you from this cosmic radiation that's out there, because there's usually no atmosphere around the other planets and moons. And also, it could just shield you from little meteorites, which are really violent. That don't need to be small, but they're really fast, so they have lots of destruction potential. Well, this would be an application why we would study lava tubes. Before I talk about all those planets and moons, let's just look at eruption stars from volcanoes that exist. The first type is explosive. As you can see in here, that is the kind of the volcano that you are familiar with, which you always see in pictures and videos. It's a steep, mountain-like shape, and when they erupt, you always see like a big cloud. That's that ash cloud, and you can also see those are kind of layered. That's why they're actually pretty tall, because all that stuff that's coming out in here in those clouds just deposits around it and makes them really tall over time. The other type is more effusive, and this is typically for shield volcanoes, which the name already implies. They're really flat, like a shield, and they extend over tens of kilometers, really wide. They don't have a steep slope, so they don't appear really high in the surroundings, but they're pretty large, and that are actually the largest volcano that we have on Earth. So let's look at some explosive volcanoes in here. That's one volcano that I have visited last year in Guatemala. Unfortunately, I wasn't there when this eruption happened in September. Would have loved to see that, but you can see in here, when this erupts, should automatically. You can see this is the ash cloud that's coming out, just shooting out in the atmosphere. And on the sides of this, you can see sometimes there's material going down, which we call pyroclastic flow, which is just like an avalanche of really hot rock and dust just rolling down the hill. There's everything that's in the way is just going to be destroyed. So probably behind this side there has been one going down. And this is what you usually see from volcanoes in here. Okay. So just a sketch of that. So this is one of those volcanoes, usually around 3 kilometers high, so they're sticking out from the surroundings, about 3 kilometers. You can see the width is not that wide, 6, maybe 20 kilometers on the base. And on those big volcanoes, can also be little craters, which are called cinder cones. It's just like a little mini volcano on the side. And why are they explosive? The reason is that there is, in that magma that's coming up, there's some sort of water dissolved in the magma, in the structure. And once it's getting up in that conduit, which is just basically a pipe that the material goes through, and once it's coming up to the surface, there's not enough pressure anymore to keep that water in the structure in the melt, so it makes bubbles. And the further you go, the bigger they become. And at some point, the pressure is really high, just as you do it with one of those pots when you boil some water. You should see, you would just press it down and you open it up. It's having a lot of pressure inside of it. It just happens here. The plug on top just pops out and that volcano erupts because of that pressure. You can see also in here that this was somewhere down here, just like a liquid. And in the end, it's turning out to be more actually some gas atmosphere with dispersed little fragments of rock, basically. And you see that in everyday life. And here in this little Coke bottle, you can see, maybe you shake it, and then you open up the top, the cap, and this is when the plug in the volcano just comes off, and then you see it starts bubbling and shoots out. And this is what happens here. So it's basically a mixture of CO2 in that case and some soda. And once that has been done, you can also see that not actually a lot out of your bottle is missing, because it's more air that's coming out than actual material. So this is a good analogy how you could think about how this happens. Okay. But not everything is really violent on those volcanoes. It can be also non-eruptive. So in here, this is Pacaya volcano. It's also in Guatemala, which is really close to the Fuego that we have seen before. And you can see it's just flowing out. And here, people do stupid or funny things, roasting a marshmallow on it or something, and then eat it. So you can see this doesn't really oppose a threat to you. It's just really coming out and kind of just like really slow doing stuff, so nothing dramatic. And it gets really hot too. Okay, so the other type is then the shield volcanoes, the effusive style. And this is a picture that we have taken last summer when I was with my advisor Alan Whittington in Hawaii to sample some rocks. And this is Mauna Loa, so you can see this is not as steep as it was before. It's just kind of like really flattened out, and this just extends over the, like if you would just continue, it just flattens out. You can see really a cone in this case. And here's a little, just the same thing, just a sketch. You can see the width on the base is really large, so up to 100 kilometers. That's just fine. And you can see in comparison, this is one of those stratovolcanoes, those normal ones that you're usually familiar with, how small they actually are in comparison to those shield volcanoes. Let's look at some eruption styles on Hawaii. You can see, and here this is on the east rift zone in Hawaii, so that means there's a rift zone where like there's an extension, so rocks move away from each other, and then there's a crack opening, and from that crack, material, hot material, the magma comes out through it and just fills up. And it also does bubble in here because there's also a little bit of water in the structure or in the melt, and but it's not as violent as an explosive volcanism. And you also can see in that video in here that it was really flat, so there's really no big cone. Also in here, another view, and then we have a closer look to that. Cracks. You can see how flat this is. There is no really high topography, and lava flows just coming down from the hill. And this is the view. It's probably just a few meters up in the front and not much more in the background in here, but you can see how that material comes out. It just like comes out like this, and then cracks open, and it just spills out to the side and flows away. And this is just a small scale, and this can be on much larger scales, and then like the whole areas are going to be covered. And this is how shield volcanoes just like become so flat and wide. And this would be an example for the larger scale. You can see those trees in the backside, and then how the lava just flows down back into a crack, just goes somewhere else. Everything that's around it will just go. There's no way to escape if you're somewhere in between. Unless you have a helicopter or something. Okay, so as I said, also in effusive volcanism there can be those bubble bursting events, but those are just typically because of water content up to 1% in total. So what's the material that's actually coming out? I should tell you. So we call this basalt whenever it's like really that dark and black, and it can change its chemical composition up to a rhyolite, which is another volcanic rock, in terms of the SiO2 content. So it has really not much SiO2 on that side, but a lot in here. And what happens is this stuff on that side is really like water, it's really fluid. And the more SiO2 you have in that lava, the more stickier it becomes. So it becomes like syrup or molasses or something. Let's have a look at how this flows a bit closer. So This is the lava project from Syracuse, and what they do is really amazing. They pour out lava on sand, for example. You can see it comes out from here, and it just flows in here, really slow in this case. It's around 2,500 Fahrenheit, which is pretty hot. You see it's flowing in here, and then it forms a crust. And it moves really slow in this case. And you can see this is the crust in here, it's really black, but there's stuff coming out underneath, so obviously in the middle, in the center of that flow, it stays hot, and because this stuff is really insulating, so it stays molten inside. You can crack up that shell. I have done that in Hawaii, and then you can just sample that liquid lava out of there. And you can see it in here again, so there's a new batch rolling down here, and it's really hot glowing, really bright, and then it cools down, becomes really dark. And then it makes that shell. Also, in another case is that what happens if the lava flow, there's like a step or increase in slope wherever your flow goes. You can see that it is up in here, really slow, and then wherever it's steeper, it flows a little bit faster. So, and then it cools again. This in here is some contamination in here. That's just a bubble. So don't worry about that. But you can see in here it flows really fast in here, and then it becomes really slow again. So obviously, a slope, like the substrate, how is it oriented, is a factor how lava flows too. So, and actually, those people estimate the lava emplacement based on the temperature that it has. I will talk about this later. The chemistry and density of that material, also the gravity. You think about other planets and moons, they have different gravity, and the thickness, and then the slope. So those are all factors that are important for lava flow and placement. So, question for you guys now. Now it's ice that they pour lava on. What would you think happens now? It freezes instantly, or explodes. All right, let's just have a look. Same stuff, same temperature, just on a different underground. So, see, it doesn't turn black immediately. Instead, it actually starts flowing around it and starts to bubble. And this is because of that water vapor that's now going to be created underneath it and just like tries to escape and makes those bubbles. And looks like it's boiling, right? So it's really funny. And it doesn't necessarily mean it doesn't flow as far as the other ones. So you can see it's pretty like dynamic. It just moves up in here and makes this little, or actually big glass bubbles. So it's really neat. Okay, so let's summarize what we just have observed. So we see that lava moves like a fluid, so just like water or syrup when it's very hot, and it can lose its heat, then it just becomes like black and makes a shell. And this is the crust in here, and the interior can stay hot, as you can see in here. This might be one of the crusts, and then it stays pretty hot inside. And at some point, this looked like it stopped moving, but it actually doesn't. And the other thing that you could not see was, if that cools slow enough, crystals are going to crystallize in that melt. So this is a different project that I worked on, where I basically created some stardust in the lab here at MU. But I'm going to show you this video. So imagine this orange stuff is the lava, and in between here those bright spots are crystals, and they're going to grow when the temperature is lowered and over time. So just look at this. So you can see how big they become. And this is just recorded with the normal camera. This is how it looks like. There's no special tricks with it. So you can see they just spread out, they grow, and then at some point it's all solid, basically. And why this is going to glow, I will explain this in a little bit. But this is also what's going on in lava. It's just not a liquid. It's basically a mixture of liquid and some solid particles. Okay. Now that I've given you an introduction how lava flows, let's just now look at different bodies in our solar system. So, how do we know there's a volcanism? So we have to look at it obviously. And how do we do that? So we could just do remote sensing, use a telescope, just point to it and maybe observe something, or send a spacecraft to that body and let it orbit with cameras, radar, and spectrometers, measure the heat in this case, or we just do manned missions, as we did with the moon, where we sent in the Apollo missions people up to the moon and collected rocks and brought them back to Earth. So the actual rocks that we have from other bodies is from the moon. We also have the meteorites, which come out of the solar system, and it was formed right up during its formation. But we also have rocks from Mars, and those rocks are because there's some or like asteroids hitting the surface of Mars. They eject stuff out of the crust or the surface, and those actually can fall back on other planets. And it happened to that they were falling, some of them, on Earth. There are some chemical composition and similarities that we find on Mars' atmosphere and in the rocks, so that's why we think they are from Mars. So we have rocks from our moon, Mars, and some asteroids. Okay. The first two things is the moon and Mercury. They're kind of like twins. They look the same. Those are just like normal color images. So this is our moon. This is Mercury, and they almost look the same. They are both gray. They are even almost the same size. Well, our moon is a little bit smaller, but it's not that different. And what we see in here is there is no volcanoes on Moon. We don't find anything that is active at the moment, but we see stuff that has been happened in the past 4 billion years ago. Well, what we can see in here is floodplains, which are those dark areas on the Moon, which is the basalt, the black stuff that I've talked about earlier, and whiter stuff, which is a type of crystal, which is anorthosite, which makes it really bright. And the same thing basically on Mercury, but in here the surface is much more cratered and destroyed, so it's not that obvious. But in that picture you can see, which is a false color image, so that's not the real color, which basically shows the chemical element distribution on the surface. You can see those blue areas correspond to the similar material that we find here on Moon in those big plains. And what are flood basalts, those big areas? Basically, it's just a large area covered with that stuff, probably from one or multitude of eruptions where that stuff just spills out on the surface. Oops, that's what I'm doing here. But we have those things on Earth too. And the closest one that we live to is here, the Columbia River basalt up in Oregon and Washington and Idaho. But they're all everywhere on Earth. And this is how they look like. There's just like layers of those basalts that just like it spills out and it sits there, becomes solid, and some other times just another flow goes over it, and it just piles up even like height of a few hundred meters. And this is how it happens. And here you can see those cracks, those fissures that are shown like in Hawaii open up, and that stuff just comes out and just spills out on the side. And this is the size basically. You can see in here in that flood basalt. But if you compare that to stuff that happens on other planets, just like Mercury, you can see here there's one single flow unit that is almost as big as the US. So, and as you saw the map earlier from the Earth, we don't have anything that is as large as this one. So that's really interesting. The other stuff or features that we can see on Moon and Mercury are those lava tubes, those pictures that I've shown earlier. And here you can see there's like a little hole inside. You can kind of trace a line in here. This is the tube, and sometimes the roof just collapses. That's when we actually can look inside of those stuff. Then we have those sinuous rills, which are basically wiggly lines. And those are probably because that stuff that's coming out is really hot. It's eroding some of the underlying ground and just like eats it away once it's flowing through. Or it could just be collapsed tubes anyway. So there's two cases. The other parts are the lunar maria, which are those black areas of those flood basalts, which is just a Latin word for sea. Let's have a look at Venus, which is our twin, almost similar in size to Earth, but it's totally different in here. This is also false color image. It's not the real color, which is basically a radar image, and you can see those brighter areas are higher topography, and whatever is darker is a little bit lower. You can see there's something that is high, that's like extending or like almost a whole hemisphere, and here also like topography map, low plains, higher surfaces around it. And what are those? Those are those big lava flows you can see in here. And those can extend up to 1,000 kilometers, which would almost represent a distance from St. Louis up to Washington, D.C. or the East Coast. So, and we don't have that on Earth too, so it's really, really large. You can see those sinuous rills. We find those on Venus as well. They're just really long, and also those floodplains. Then we have large volcanoes, and those volcanoes usually occur in volcanic centers. So there's not just one single volcano, there's really a bunch of them around it. Population up to maybe 50 or even 100, not in a big area distributed. They're really condensed on one spot. And once they erupt, they also create really long, large lava flows going down here. So this is a little bit exaggerated in the height. Usually they stick around like 6 kilometers from the surroundings. So it's equal to what we see on Earth, maybe a little bit higher than what we see here, but those lava flows are really long. And here is one of those areas where we have like little volcanoes concentrated on one spot. And this in here is like a pancake structure, which is lava domes just sticking out from the underground. And those are not large, but they're almost like 20 kilometers across. So they're small, but they occur like all over the surface in those areas. Here's a nice picture from the surface of Venus taken by a Venera spacecraft back in '82. This spacecraft just survived a couple hours because the atmosphere of Venus is terrible. The pressure is 90 times higher than on Earth, and it's a really hot temperature up to 470 degrees, which is around 900 F. And that's not enough. There's even sulfuric acid in the atmosphere, so everything that's sitting there just gets eaten away from the heat, from the pressure, and then from the acid environment. But you can see those are the rocks in here, so it's a really nice picture. This is how Venus looks like. All right, let's go to the next planet out of the solar system is Mars. And the really extreme thing on Mars is those large shear volcanoes. So as you think about the ones on Earth, they are large, but on Mars they're even larger than that. What you can see in here, which is Olympus Mons, which is up to 20 kilometers high from its base and really hundreds of kilometers wide. And even the smaller ones are large. And we can compare those with the ones on Earth. We can see in here, this is Earth, and then we will have Hawaii here. That's the video that I'm going to show. And this gray spot around this is the Olympus Mons from Mars, just overlay, and you can see how small Hawaii, our biggest volcano on Earth, appears next to it. You can see the greenish in the middle, that's Hawaii, and this all here is Olympus Mons on Mars, so this is huge. Although this planet, Mars, is just a quarter size of the Earth, right? So you would kind of naturally not think those big things would occur on a smaller planet than Earth, but it does. And the latest volcanic activity on Mars is about 50 to 200 million years ago, which is in geologic timescale just like yesterday. As seen on Mercury and Moon, it's almost 3.5 billion years ago. That is quite a long time, but this 2200, that's just like yesterday. So we could think about that Mars is still volcanic active, although it stopped maybe 20 million years ago. Okay. And the same features in here too. We have those really extended lava flows, which you can see in here. This distance would be 100 kilometers, and you can just like add it up. That's up to almost 1,000 kilometers lava flows. The same thing. Also find those sinuous wells and lava tubes. This is a surface picture of Mars rover Curiosity taken back last year. So you can see this looks more like a desert. You can see light, you can see rocks on the ground. And it's really cold up there, and there's no really atmosphere that we can breathe in. It's mostly CO2. The last one, that's the moon of Jupiter called Io. And this is the most active volcanic body in our solar system. It's really small. It's around the size of our moon. And the surface in here is really young. It resurfaces, so there's always a new surface around or on that body in just a couple of years, because it's so volcanic active that it's just like one lava flow over the other one, so there's nothing really old on the surface. And the other really cool thing about Io is that it has this crust around it, not really thick, but underneath it there's supposed to be a magma ocean. So compare to just the water ocean that we have on Earth. In this case, on Io, it would be just made out of molten rock, which is really crazy. And the reason for that is it's really close to Jupiter, which is our largest planet in the solar system. And it has lots of gravity around it, so this moon is really close to it. So you can imagine that there's a strong pull from Jupiter on that planet, on that body. And then also it rotates on one axis, and every time it faces, or the face towards Jupiter, it gets pulled. And this pulling causes so much friction that this stuff just heats up or even stays hot and doesn't cool down. So, because if you think about it, Moon is really small, Mercury is really small, but they are not volcanic active. And this one is even smaller, but it's still, just because it has this called tidal heating effect because of Jupiter. Other type of volcano that you can see in here is not just all rocky. Can be also a volcano that's shooting out liquid sulfur. So there's other types of volcanism. But now I concentrate on rocky volcanism. But it also could be cryovolcanism, which is just water or ice. Let's summarize this. So only 3, Venus, Earth, and Io, of the terrestrial bodies in our solar system. There are more, but just those 3 are volcanic active. And let's include Mars too, but we know right now there's no evidence that it's like lava flows at the moment. Whereas the other 3, there is ongoing volcanism right now at the moment. And all those features on those bodies are really extreme. We don't find those on Earth. So this is surprising because of the chemical composition and all a little bit more complicated than I was showing it before. You would not really expect those lava flows to be that long. You would think they might stop earlier, but they are not. So this is really interesting, and we don't really know why this forms. And that's when we do research. And how would you do that research? So this is basically my job here that I'm working on, is to look at the effect of physical properties. So one thing I'm going to talk about is temperature, and then we have the chemical composition and crystallinity. So when it's cooling down, the viscosity, how sticky that stuff is, goes down because it's cooling down. Just as you think, just like hold a candle in your hand, it becomes warm, you can deform it, just lay it down, it cools down, it's just kind of brittle, it would break. So this is the effect of viscosity with temperature. And then once it's cooling down, and it's cooling down slow enough, it can crystallize. And what then happens is the crystals appear, and they take out components, and the actual lava changes its chemical composition. So there's a feedback relationship in here. The other part of it is the thermal properties. So think about this crust. You have seen that it's underneath still liquid, where it's solid on the outside. So obviously there's a kind of insulation once there's a crust that it can stay hot. And this is the other part that we are interested in. How insulating basically are those materials? Lots of people always ask me, so you have rocks from Moon and Mars and all that stuff? And I was like, oh, I wish, but they're really valuable, so I would never get one of those, so I have to make my own. And how I do this is I just put those oxides together, mainly SiO2 and then some iron oxide and magnesium oxide, and just heat them up and melt them in here. You can see I just have those pieces, the glass on here, and then we melt it in that little cup, which is made of pure platinum, which is really expensive, but it's durable under that conditions. And I make my own rock, and then just pour it out once it's like totally molten, and then make those glasses. And once I have those glasses, I can do lots of experiments on it. And the most interesting thing about it is viscosity. And this is the resistance of a fluid to flow. And I will demonstrate this with this diagram here on analogies from everyday life. So let's do this. So there's something called Newtonian fluid, where we have a stress and a strain rate relationship just linear. So I can apply as much strain, just like I would just pull it or just squish it. And the stress is just linear to it, and nothing really happens, just like water. And the other case would be this green line here, which would represent shear thickening. So I have something in here. After the talk, you should come to the front, which is called bootleg, which is whenever I apply some stress to it, it becomes solid. And when I do something really slow with it, it's a liquid. And I can demonstrate this in this video in here. So on that side, that's just a water bucket. And this is this oobleck stuff that I have right here. And there's a person now dropping a wrench into it, and then imagine what happens. It just falls down here, sinks, as you would think. In this case, it just stops, sits there, and once that falling stress, when it's hitting the surface, is going away, basically, it just can't sink because there's not as much stress anymore, and that becomes like a fluid. Right. In this case, you can just whack it. You can see it doesn't deform. You even could see it. But it's just whacking it. It doesn't deform because it's like a solid. But whereas you push slowly on it, when you formed it, you can actually deform it. And in here, person punches it. You can do this as well. You can see it's like a solid. But if you put your hand really slow, just put your finger in it. This could but there's a spoon in it. You can see in here. Just should come in the front afterwards. But it doesn't go down. But if I do it really slow, you can see the spoon sinks into it. We'll just come afterwards and play with it a little bit. A little bit messy. Should be fun. Other example would be here. There's a water balloon filled up with water, and what happens if you just drop that down to the floor is it just deforms and just wobbles with the form basically of the water balloon. And that's the same thing with oobleck, because there's now, once it's hitting the surface, a really strong stress that you apply to it, and then it becomes just really solid, just like in here. It doesn't really deform at all. Okay, the other thing is shear thinning, and you also know that from whenever you go to a restaurant and they give you a glass bottle with ketchup, and you're like, oh my god, I never get anything out of this because it just sticks in there. And what you naturally do is you shake the bottle, and then you will see the stuff is coming out, because then you apply that shaking, the stress to it, and it becomes fluid. And it's just the other way around, which would be that line. And there are obviously 7 tricks that you can do to make ketchup a liquid. See, just shake it and then it's coming out. If you just hold it, it maybe drips out, but most likely it just stays in the bottle. Just do it like this. Should do that in a restaurant. It might just like slip out of your hand. Could be not nice. But this in here is interesting. So you see that woman holds it underwater, and this is the thermal effect on material when you heat it up. That it becomes more fluid. And we'll demonstrate this to you right in just a second. The other case is a Bingham fluid, which is representing in that line. And you can see this is again just like a oil or a lotion out of a tube, and you just squish it and it just makes a rounded surface just because of the surface tension. But if it has a yield strength, which is like a minimum stress that you have to overcome to deform something, it basically keeps its shape, so it doesn't really deform. If I would now use my finger and just squish it, then it would deform, because that is the stress that I have to overcome that it actually deforms. And then the last case would be this line E, which is partially a bulk plate fluid. Basically, it's a mix of that toothpaste with the oblate. It's just like it has a minimum yield strength, and then once you apply more and more stress, it becomes solid. Right? So how would I measure this here at MU? We have a technique that's called concentric cylinder technique. And it's basically a platinum cup with a platinum spindle. You have your melt in it and a furnace, and you just heat it up down to there where it's glowing. You can see this. And then you start rotating that spindle, and with the angular velocity of your spindle and the exerted torque on that spindle, you can measure the viscosity. So the resistance of that material to flow, you can see it's spinning in that melt. And this is actually a composition that I have made for Mercury. Okay, the other way is we can do this at much lower temperatures with the parallel plate technique. So we have a little sample and we just squish it, just as we do, or as I could do with this Play-Doh, and also heat it up into a furnace. And you know this from the summertime, New Street, it was really hot. Trucks go over it and it just deforms, just because of the own weight of the cars and trucks that go over it. So this is also how you could measure viscosity. And it turns out that those things at higher temperatures are like an order of magnitude different from what I have observed so far. And you can see this is not a linear relationship. This goes up into here where we have lower temperatures. Between 600 and 800 degrees Celsius, where we have 10 to the 12 Pascal seconds. At this point, we usually say things behave more brittle. I could still deform it in here, just like the Play-Doh, but it's really slow, but it's still deformed. Once I cross that value up in here, it might just not deform really slow anymore. At some point, it will crack. Right, so this is kind of a limit, and we can. This is on a time scale where we can observe it, but it still behaves like it just moves away over a much longer time scale. But we just it would take too long for us to observe. Things can be solid up in here, but still behave just like this, like a liquid. So, the other thing is, as I showed earlier, lava may crystallize if it goes really slow, or if you just hold it at some certain temperature where crystals could appear, and they would just grow over time. And this is just an analogy here for a lemonade. Let's see, it's at room temperature, it's liquid, and once you freeze it, basically make this slushy in here, you have the crystals in it. In this case, I have to be careful what to say, because those crystals are just made of water. In magma, it would be a different composition, just to be straight here. But what you also can see in here, this surface is flat, right? Whereas this surface that has topography just because of the addition of crystals. So you can see this is kind of that tooth-based behavior that I showed earlier. And in fact, I can see that in some data. So this is the Mercury glass that I've created with some crystals in there. And this is a data set for a rock from Hawaii, which would be black, but it almost looks like this. So there are crystals in here. But you can see it's not going through the origin, so there's a little yield strength that I have to overcome to actually form it. And the more stress I apply, it looks linear, but if you make this a little bit smaller, that diagram, it turns out to be a slight shear thickening in here. And this is just at a certain crystal fraction. I still have to investigate what happens whenever I have more crystals and what are actually the crystal sizes in here. The last thing, the thermal budget. So how insulating is that stuff actually? And what happens when stuff crystallizes? So when magma or lava crystallizes, crystals grow, but what also happens is, because the lava is kind of a random structure, and the crystals are really defined, like atoms are really packed really nicely in a really nice order together. So that means it needs less energy in the end. And that energy that it had from the transition from a melt into a crystal structure isn't needed anymore, so it has to release it somehow. And it releases it as heat, and this is why those little crystals grow. And I will play this video again. You can see once they're growing on the outside, it's really bright. And this is just the heat that you can observe. It just heats up a lot. See? This is the crystal front, and it's really bright on the outside, and inside it gets darker again, just cools it down. And what we're doing here is, because it's liberating that heat, we actually are interested how much heat is that's going to be created. And I told you earlier that the lava viscosity, so how sticky that stuff is, depends also on the temperature. So if you look at the lava flow, once it's cooling, but then it's crystallizing and releasing heat again, how much is that heat? And can that heat actually buffer the temperature of the lava flow, that in the end it can flow much longer? Or does it even heat it up at some point? And maybe that the lava flow can flow longer because it's hotter, or it flows easier because it's hotter. But also it's the thing, once I add crystals, viscosity also increases. So there's a balance that we have to try to figure out what is actually weighing more on the viscosity. Is it thermal effect or is it crystal? And we do this with calorimetry, so we just heat up a little sample. It's not bigger than a piece of a couple of grains, just a milligram sized pieces. And we heat that up, and at one time we just measure a signal in that calorimeter, which we just got new, and we see how the heat basically changes, or whenever we see a signal from a transition from like a crystal structure into a melt structure, we see there's a heat flow, and we just can detect that, and then we can actually relate this, how much this would be, and at what temperatures. Okay, and just another picture in here. So once we know those things, how much heat is created, we also can measure things from the crust, how insulating, how fast heat can go through, which is conductivity. There's Professor Hofmeister at WashU in St. Louis, which I work with quite a lot, and she does that thing. So all my samples that I'm going to create, I will send it to her, or even do it with her together, and measure how fast heat can actually go through this, that this might inside stay hot even longer. Okay, so let's just summarize this now. So you should have now, by the end of the talk, an idea about the types of volcanism, so that we have explosive versus effusive, and what types of volcanoes they create. The type of the erupting material, it's usually a basalt, and the morphologies that it develops, which are floodplains, tubes, and those rills. Then that there is extinct volcanism, basically on Mercury and Moon, and active volcanism on Earth, Venus, Io, and let's include Mars. And the last part was that I have told you about lava dynamics, so the emplacement, how lava will flow, and what it depends on. So the viscosity, then you had crystals, then they crystallize, then they release some heat, and all that interplay. That's what's basically going to happen in a lava flow here on Earth and also on other planets. And thanks for your patience, and we'll happily to answer your questions. And please come play with Blake. It's really fun.
Do you have any questions for us? That's it all.
Where are you from in Germany?
The north part of Germany, Hanover, specifically where I grew up. Familiar with? Yeah. Other questions?
What
influences the chemical composition of the lava? Is that something it picks up, or is that something?
That is already in the lava, so whenever it's like in the underground, when it's macro,
So the effect
it's already melted in there. It tends to the rock.
So the liquid, whatever under the crust of the earth, it has different compositions depending on where it's from.
Yes, more or less
That's why I wanted to do from the crust.
Nice job, Alex. I'm sorry. Anyway, so I think that how many activity on
I actually not.
that there's active tectonics going on. I think you're right. So, volcanism is not implied. I got excited.
Like,
Oh yeah, man.